Okay, here the recording in progress. So let's share the screen. Okay, so we're here. Sun is a lot brighter now after we changed our clocks, so more sunlight in the morning. We have a short week. Friday is a holiday for Veterans Day. For us, I realize that's different. Some people celebrate Veterans Day right on the 11th, but I guess for us, that's not true. So we're still meeting Thursday, the 11th, and Friday's our Veterans Day holiday. So that being the case, our quiz is on Thursday this time. So quiz Thursday, usual rules, due at 11:59 p.m. And you should have gotten a reply email back from me about the most recent quiz. If you did not, then let me know. And I also sent over the weekend the solutions for that quiz and change and error that I made on that also, okay? I've already finished 11.3, so I'm a day ahead, looks like. We're starting 11.4 on the comparison tests. A reminder, I sent you a Canvas announcement earlier about the CSM Math Resource Center having some workshops on the comparison tests. You're welcome to join that. You don't have to, you're not required to. You don't get any extra credit for it, but it's just if you think you need more help on the comparison test, which is what we're doing presently. Okay, so let's jump right to the comparison tests. Let's see what we got. Okay, let me show you the problems. 11.4. We have to do what? 3 to 31, 3 to 31 odd, 11.4 there. Here we are. Page 731. No, it's crooked, but sorry. I have to, the arm of the document camera is in the way, so I can't get past that. So we're just testing for convergence or divergence. Once again. Right, so we've talked already about the comparison test, CT. The wording that Mr. Stewart, the author, has is not quite the same as what I have, but it's equivalent. I'll show you my version shortly. Then you also want the limit comparison test. So put LCT, limit comparison test, page 729 on your cheat sheet. And this is actually more useful. It's harder to understand, comprehend, I suppose, but it's useful in more situations than the regular comparison test. Okay, suppose summation of A sub n and B sub n. Notice the lazy notation of not putting n equals 1 to infinity or whatever, that's still okay. Suppose they only have positive terms and the limit as n approaching infinity of A sub n over B sub n is C. C is a finite number greater than 0, meaning the limit exists and it's positive. Then either both series converge or both diverge. That means whatever happens to one series happens to the other. So if one converges, the other converges. If one diverges, the other diverges. It's a pretty strong theorem. Okay. And this limit can be any positive number. Okay. So it cannot be 0. It cannot be infinite. And the limit has to exist. It can't be undefined. Okay. And we'll see how that ends up working. So now for my analysis, get back to where we were. So I'm not doing any problems yet. I'm just going to give you some background. So this is where we were last time. Here's the A sub n series, B sub n, A sub n less than or equal to B sub n. Okay, so summation of A sub n diverges. The smaller series diverges, then the bigger series diverges. Then summation B sub n diverges. And on the other hand, if the larger series, summation B sub n converges, then summation A sub n also converges. Right? Summation B sub n diverges. The bigger series diverges. No conclusion. Summation of A sub n converges. Smaller series converges. No conclusion can be made, right? I gave you an analogy last time about people with money or something like that, right? All right, so new stuff. First, let's go over the reciprocal rule. Okay, you probably already know this, but maybe you haven't heard it formally. So we'll state it formally now. For positive numbers A and B, if A is less than B, then 1 over A is greater than 1 over B. the reciprocal rule, the flip. Okay, here's a simple example. 2 is less than 3. You know that, right? So if we reciprocate, the inequality goes the other way. 1/2 is greater than 1/3. So if you have half a pie, it's bigger than 1/3 of the pie. Okay? So we'll be using this quite a bit, the reciprocal rule. Okay? So if A is less than B, then when you flip them, 1/A is greater than 1/B. All right, so let me show you this. N minus 1 is less than N, which is less than N plus 1. We know that, right? For any N. Therefore, by the reciprocal rule, it goes the other way. 1/N minus 1 greater than 1/N, greater than 1/N plus 1, using this reciprocal rule. Okay, now what do I know about summation of 1/N? Well, that series diverges because it's the harmonic series. Therefore, by the comparison test, any series which is term by term bigger than that will also diverge. So summation of 1/N minus 1 also diverges by the comparison test. Okay, so follow this logic. This series diverges, blows up. Term by term, this one stays above this. This one blows up. So this one has to blow up also. In other words, it obeys this. Okay? We have a series which diverges. I got another series which term by term is larger than a series which diverges. It also has a diverge. How about summation of, so we would say summation of 1/N minus 1 also diverges by the comparison test, but summation of 1/N plus 1, no conclusion can be made, at least not yet. Okay. The bigger series diverges. What about something smaller? Can't tell, right? The bigger series diverges. Okay. Summation of B sub n diverges. No conclusion about A sub n. It still might diverge, it might converge, right? The analogy is we have less money than a billionaire. Okay, if I have less money than a billionaire, are you rich? Or, I don't know. That might mean, $999,999,999, or you might have $1. We can make no conclusion. Okay. If I say you have more money than a billionaire, okay, that clinches it. They're rich also, right? So that's sort of what's happening here. Okay, now let me show you this companion series. Okay, n squared minus 1 is less than n squared, which is less than n squared plus 1. We know that, right? If you subtract 1, it's smaller. If you add 1, it's bigger. And therefore, by the reciprocal rule, when I flip them all, it goes the other way. 1/n squared minus 1 is greater than 1/n squared, greater than 1/n squared plus 1. Okay, what do I know about summation of 1/n squared? Converges. How come? P series, P equals 2, which is greater than 1. Therefore, any series which term by term is smaller than that will also converge by the comparison test. So therefore, summation of 1/n squared plus 1 also converges by the comparison test. Okay. The picture would be this one. The bigger series converges. The B sub n's converge. Therefore, the A sub n's also converge. Okay. So that would be like saying, I have less money than that poor person over there. If I have less money than someone who's poor, I'm also poor, right? But we cannot make a conclusion the other way. Summation of 1/n squared minus 1, no conclusion. Okay, where this series converges. What about this series term by term, which is larger? No conclusion. That picture would be like this. The summation A sub n converges, no conclusion. This one converges. What about something bigger? I don't know. That's like saying, I have more money than that poor person. Okay, you could still be poor, you could be rich, you could be a millionaire, you could be middle class, whatever. You can't make any conclusion, right? Okay, I have more money than that poor person over there. I still might be poor, or I might be a millionaire, right? So that's the way the comparison test works. Okay, now, limit comparison test. So when I had this, I could say that 1/n minus 1 diverges but I couldn't say anything about 1 over n plus 1. Still, you kind of look at this and say they all behave somewhat the same, right? It feels like this series still ought to diverge because its nature is very similar to the harmonic series. I couldn't prove it with the comparison test. Likewise, it feels like this series should still converge because it's kind of like summation 1 over n squared. That -1 doesn't change it significantly. It still feels like it ought to converge. I can't prove it with the comparison test. That's where limit comparison test comes in. So now here is the limit comparison test, LCT. Okay, it's harder to understand, but it's actually more useful. All right, so here's my version. Given summation A sub n, summation B sub n, notice the lazy notation, not putting 1 to infinity, it's not necessary. And you have positive terms. You take the ratio, limit n approaching infinity of A sub n over B sub n, which is C. The only requirements for C is that it's not 0 and not infinity. That's a lot of numbers. It'll be positive because you only got positive terms here. And the limit has to exist. So the only times you cannot use limit comparison test or if the limit is 0, infinity, or the limit doesn't exist. Then both series converge or both series diverge. That's kind of like the integral test. Okay? Whatever happens to the integral happens to the series. If one converges, the other converges. If one diverges, the other diverges. Likewise here. You have two series that satisfy the hypothesis of the limit comparison test. Then if you find one series to converge, so does the other. Or if one diverges, so does the other. Okay? And here's an example of how to use it. So if you can change the series into something you quote unquote recognize, and then use the limit comparison test, then you say whatever happens to one happens to the other. Okay? So for this one, summation of 1 over n plus 1, the one where I can make no conclusion, I can make a conclusion if I still compare it to the harmonic series and use the limit comparison test. So how does it work? Take the limit as n approaches infinity of 1 divided by the other. So 1 over n plus 1 divided by 1 over n. So how do you know which one's on top and which one's on the bottom? It doesn't matter. You can't be wrong. Okay. So let's say if one way the limit came out to be 7, that works. If you went the other way, the limit would be 1/7. That would still work. It's still not 0. It's still not infinity. So you can't really go wrong. Say, how do I know which one to put on top and which one to put on the bottom? It doesn't matter. Okay. All right, so I take this limit. 1 over n plus 1 over 1 over n, multiply top and bottom by n. So I get n over n plus 1. By L'Hopital's rule, that's infinity over infinity. So I get the limit as n approaches infinity of 1 over 1, which is 1. Okay, and that's fine. Okay. So by limit comparison test, I got a limit that came out to be 1. I guess that's the ultimate in closeness. Okay. The two series are close to each other and that the limit was 1. Okay. Now, if two things are equal, we say one is a fraction equal, right? If I have a fraction that's equal to 1, that means the top and the bottom are equal, right? This is about as close to being equal as you can. They're not equal, but they are in the limit as n goes farther and farther to infinity, right? You know, look at this expression. Plug in a billion over 1,000,000,001. We would, for the most part, say that's practically 1, right? So the limit is 1. Therefore, whatever happens to one series happens to the other. And we know summation of 1 over n diverges because it's a harmonic series. Therefore, the summation of 1 over n plus 1 also diverges. I could not use the CT comparison test, but I can use limit comparison test. Okay. They are alike. And what do I mean by alike? The ratio as n approaches infinity approaches 1. It doesn't have to be 1. It can be any positive quantity. Okay. And you can do something similar for this one over here. All right, that being the case, the more useful rule usually will be the limit comparison test. And I'll get started with some problems with that right now. Because the first one is supposed to be 3. It's really 3 star, I guess. Yeah. I'll do this one. 3 star. Summation n equals 1 to infinity of n over 2n cubed plus 1. Okay. Now, a good strategy to think about this is to say, okay, when n gets super big, what becomes insignificant? This +1 becomes insignificant, right? So it's essentially like n over 2n cubed or 1 over 2n squared. You can forget about the 2. That doesn't change convergence or divergence. So I will choose my comparison series to be summation of 1 over n squared. That ought to do it. Why do I pick this one? Because I know this one converges because it's a convergent P series. In fact, I just did that over here. Right, remember the rule for P series back on the section on the integral test. Now, you actually have to prove it. So limit n approaching infinity. I take this one divided by this one, n over 2n cubed plus 1 divided by 1 over n squared. You could put this on top of that. That also works. And let's see, multiply top and bottom by n squared to cancel that out. That gives me limit n approaching infinity of n cubed over 2n cubed plus 1. That's infinity over infinity. Therefore, L'Hopital's rule applies. Take the derivative of the top, derivative of the bottom. Limit n approaching infinity of 3n squared over 6n squared. That's 1/2. That does satisfy the hypothesis of the limit comparison test. Okay, I took the ratio, I got 1/2. Give me any positive number, just so long as it's not 0, not infinity. And the limit exists also. Therefore, whatever happens to one happens to the other. But you see, I'm comfortable with this. See, I don't know what happens to that, but I know what happens to that. So LCT says, whatever happens to one happens to the other. They both will converge or they both will diverge. So what do I know about summation of 1 over n squared? Whoops. It converges because it's a P series. P is equal to 2, which is greater than 1. Therefore, the original series, so S is our abbreviation for the original series, just like before I used capital I for the original integral. The series also converges by LCT, limit comparison test. All right, here's another one, number 5, which I think does match ours. Yes, this matches ours. Whoops. Okay. Summation of n plus 1 over n, and yes, no, I got lazy. I didn't put the n equals 1 to infinity, but usually for these kind of problems, you don't have to. Okay, when n gets super big, what drops into insignificance? The 1, right? So I cover it up. By the time you get n to be millions and billions and trillions, that plus 1 is insignificant. I just look at this and say, oh, n over n radical n, cancel the n's. It's like 1 over radical n. So I compare it to summation of 1 over radical n, which is the same as 1 over n to the half. So I think this behaves like this in the long run, which we can now prove. So take the limit of n approaching infinity. So either one on top, either one on the bottom, doesn't really matter. So how about I put n plus 1 over n radical n divided by 1 over radical n. Multiply top and bottom by radical n. They all cancel out. And I have this. And this fits the category of L'Hopital's rule. So n gets big, it's infinity over infinity. Take the derivative of the top, go to the bottom, 1 over 1, 1. So it is true that the limit of the ratio of the terms is a constant positive quantity. So whatever happens to one happens to the other, but I know what happens to this. Summation of 1 over n to the half, that diverges because that's a P series where P is a half and that's less than 1. Rule for P series. Let's see if I can resurrect that back here. That was section 3. Page 722. P series, summation of 1 over n to the P, convergent if P is greater than 1, divergent if P is less than or equal to 1. That was on page 723. Okay, the next one actually requires comparison test. Summation k equals 1 to infinity, ln k over k. Okay, I don't really recognize that as anything. However, when k gets bigger and bigger and bigger, that's certainly bigger than 1 over k. Okay. I think I should add this is for k greater than 2, I believe. If ln2 is smaller, I think it's 0.693. But in the long run, eventually, this is true. Okay, and why do I want to set up this way? I know summation of 1 over k diverges because it's the harmonic series. Okay. The smaller series converges. So the picture, it's like this. The smaller series diverges. Sorry. Therefore, this one would also have to diverge. Okay, summation 1 over k diverges because it's the harmonic series. Therefore, ln k over k, or you can say the series, also diverges by the comparison test. Okay. Okay, 13 star. This is not in the book. I don't see it in there, but it's okay. Summation n equals 1 to infinity, arctan over n to the 1.2. Okay, if I only look at this part, that looks like a P series. Does it converge or diverge? This one converges because the P is 1.2. It's bigger than 1. Okay, the cutting edge of convergence or divergence is 1. Okay. If the exponent is 1, that's our divergent harmonic series. But if I just go ever so slightly above 1, like 1.001, that would all of a sudden converge. Okay, what do I know about arctan? When arctan of a real big number is almost pi over 2, a little bit smaller. Okay. You might recall the arctan function looks like this. Like that. Close to pi over 2, but stays below. That's the key thing. So I'll start up with this. Arctan of n is less than pi over 2. Then divide both sides by n to the 1.2. Why do I do that? I need to make it look like this. I want to show that the bigger series converges. Okay, summation pi over 2 over n to the 1.2. You're allowed to factor out the pi over 2. And remember, multiplying by a constant does not affect convergence or divergence. Okay. So if this series converges, if I take out the pi over 2, it still converges. If this thing diverges, take out the pi over 2, it still diverges. All right, and what do I know about summation 1 over n to the 1.2? That converges. That's a P series where P is equal to 1.2. So I found the bigger series converges. Therefore, the original series also converges by the comparison test. Okay, so I took my original series, made it a little bit bigger by putting pi over 2, because I recognize that this one does not blow up. It approaches a finite number. Okay. Using this picture analogy again, I got the larger series to converge. Therefore, anything below that has to converge. We have less money than a poor person. If I have less money than a poor person, I'm also poor, right? So that's what's happening with that one. Okay, 17 is the last one I was going to show you. Then I'm going to be pretty much done, folks. I can still do more problems tomorrow. So problem 17, and that does match our problem 17. Okay, summation of 1 over n squared plus 1. I guess I should have covered this up, but it's too late now. I should have guessed. What should be a good comparison series? So when n gets real big, what can I ignore? Plus 1, right? Look at a million. Million squared is real big. So, oh, I add 1. That adding 1 is like almost literally like nothing, right? You have someone who's a millionaire, you know, you give them $1 more, or you take away $1, that should not really phase them out too much, right? They're still basically millionaires, right? The +1 or the -1 is so insignificant at that stage. So if I ignore the 1, it's 1 over n. So compare it to summation 1 over n. Okay, so I'm going to aim for the limit comparison test. Okay, so the nice thing about the limit comparison test, you don't have to worry about, okay, is this one larger than this one? For the comparison test, you do have to state for sure, oh yeah, this one's larger than this one, or this one's larger than this one. You don't have to worry about that for the limit comparison test. So I would work out this problem the same thing if it were n squared +1 or n squared -1. Okay, in which case it flip-flops which one is considered the larger. It doesn't matter. Okay, so take the limit as n approaches infinity of the ratio 1 over radical n squared +1 divided by 1 over n, multiply the top and bottom by n. And now it looks like this. Then I'll divide top and bottom by n in the form of divide this by n and divide this by n squared underneath the radical. That's allowed, right? Because the square root of n squared is n. So limit n approaches infinity, that's 1 plus 1 over n squared. And now when n gets big, this approaches 0. Sorry, 1 over square root of 1, 1 over 1, 1. Okay, so yes, indeed, I can use the limit comparison test. The ratio is 1. Like a lot of the homework problems, the ratio is going to be 1. Okay, we had one that it came out to be a half, I think. But it can be any positive number. Okay. This is the ultimate in being alike under the series. Okay, these two are very much alike, meaning as n gets bigger and bigger and bigger and bigger, the ratio is 1. Remember, when is a fraction equal to 1? Right? If I have a fraction like x over y equals 1, that's going to be true when x and y are equal. Here they're not equal, but they're very, very close to being equal. So close that when n gets way out there, it looks more and more like the top and bottom are the same in order for the ratio to be 1. Okay, and yes, therefore, whatever happens to one happens to the other. What happens to the one that we know of, summation of 1 over n, diverges harmonic series. Therefore, that means therefore, the series also diverges by the limit comparison test. Okay, and just thinking about this, you would not be able to just use the comparison test for this one because this term is less than this one because you're dividing by a bigger number. Okay, so that would be the case of, yeah, less than the divergent series, you cannot make a conclusion. That would be like this one. We are smaller than a series which diverges, then you can make no conclusion. Okay. The money analogy I've been saying, okay, I have less money than the millionaire. Okay, I still might be rich. I might have $999,999, or I might have 50,000, or I might have 5 cents. Right? You can't make any judgment in that situation there. Okay. But by using the limit comparison test, I can go ahead with it. So since the harmonic series diverges, therefore the original series, which I'm labeling this as, also diverges by LCT, limit comparison test. Okay. All right, that's as much as I was going to cover today, and I'm still a little bit ahead, I think. So I will continue on with 11.4 tomorrow. On the original game plan, we weren't supposed to start 11.4 until tomorrow, and I've already stuck some in, and I may even finish it tomorrow. So it looks like as of now, I'm a day ahead, which I guess is fine in case I fall behind later, I get sick, or the internet goes down and whatnot. That's the way we'll go with it for now. Okay, so I'm done, folks. Let me stop the share and see if you have any questions. Okay, any questions, please? All right, that'll do it for today, folks. So everybody have a good day, and we'll see you next time.
All right, take care, Professor.
Take care. Okay, bye.